Hi everyone, my name is Furkan Sen and I'm from University of New South Wales, Sydney, Australia. And it's my pleasure to present today at MIT A+D conference. And in next 15 minutes, I'll be talking about improving the technical feasibility of CO2 storage in oil reservoirs. CO2 storage in oil reservoirs is a method to reduce greenhouse gases by storing them into oil reservoir forever. But to deploy the real impact of CO2 storage in oil reservoirs, we have to apply this method at a much larger scale than what we do now. And that's what we are going to discuss today. So what is CO2 storage in oil reservoirs? So we inject CO2 deep into underground formations which contains oil. And this CO2, this injected CO2 mixes with oil and it displaces towards the production well. And because the pore space within the rock is now available for CO2, so oil comes up and CO2 remains, at least a big part of the injected CO2 remains stored in this storage rock. Now, we know that these rocks have stored oil and gas for millions of years at high pressure and high temperature. Therefore, we know that the injected CO2 will stay there trapped forever because the nature has provided a foolproof seal. Another big advantage of CO2 storage in oil reservoirs is that the cost of injected CO2 can be offset by the amount of oil which we produce with this method. Therefore, it makes CO2 injection in oil reservoirs the most economical carbon capture, utilization, and storage, or in other words, CCUS method. And that's why 75% of current CCUS projects are related to CO2 injection in oil reservoirs. Now, what do we need or what is the role of CCUS to achieve carbon neutral future? That can be shown in this graph. So this is International Energy Agency data. So it shows the global CO2 emissions in gigatons. So the first part of the graph is historical data, and the later part is predictions. So with the existing policies and promises by the companies and governments, this is where we are heading, which is not a good news for us, and it's way off the targets. But where we should be is down here, and this bottom line represents 1.8 degree scenario by 2040. How do we get from the top to this bottom point is using this. So these technologies are the solution. It includes energy efficiency, renewables, fuel switching, and other methods, including CCS and CCUS. Now, many environmental activists and other people assume that CCS or CCUS is actually a license for fossil fuels usage in future, but that's not true. In fact, it has been shown through a number of modeling projects that CCUS in fact shifts the economics in favor of renewables, especially in power sector, and therefore CCS is actually an enabling technology which enables other technology deployment as well. And International Energy Agency has emphasized a number of times that these methods are not alternates. So we must use all of these methods in order to achieve carbon neutral targets. So therefore, CCUS is an essential part of our future solutions for carbon neutral future. Now, in the previous slide, we saw we need 7% contribution from CCUS. So how do we get there? To achieve that, we need to increase our current CO2 capture of 35 megaton per year to 1.4 gigaton in 2040. It's a huge increase in CO2 capture, and that means we need to deploy CCUS methods at a much higher scale than what we are doing now. And CO2 injection in oil reservoir being the most deployed CCUS method right now, it has to be used at a much larger scale. And to do that, we need to have policy changes. We need to improve the technical feasibility of this process so we can deploy CCUS at much larger scales in many more oil reservoirs than what we're doing now. And this is the part which I would be focusing on in this talk, but I will show that this technical feasibility is not complete if we do not talk about the policy. So the policy changes and the technical interventions have to go side by side. So I will be focusing on two of the major issues which restrict CCS deployment in oil reservoirs. Let's start with the pressure too low to achieve miscibility between oil and CO2. So let's look at what happens to CO2 when it enters the rock. So let's assume this is a pore, CO2 enters into a pore within the rock. Initially, the displacement is immiscible, excuse me, and there is an interface between CO2 and oil. But as the flow continues, mass transfer occurs across the interface. So some of the CO2 condenses into oil, and some of the lighter components from oil vaporize into CO2, and that creates a miscible bank. And this miscible bank has zero interfacial tension with the oil and CO2, and therefore there is miscible displacement, and which displaces theoretically 100% of the oil in the pore, and therefore this pore space is available for CO2 to be stored. But this only can happen when the pressures are enough to achieve miscibility. If the pressure is not enough to achieve miscibility, the displacement is not efficient. It means there will be some oil left over in this pore, and that is why a less pore space is available for CO2 storage. So how can we improve this? Several recent attempts have been made to reduce the miscibility pressure requirements, and we call it modified CO2 injection, and means that we inject CO2 pre-mixed with additives. It's still, the injection stream is still CO2 rich phase. It contains probably 95% or more CO2, and less than 5% is additives, which can be polymers, alcohol, surfactants, or other chemicals. And these additives reduce the miscibility pressure by 1 megapascal to 10 megapascal, which is a significant number in terms of reservoir pressure. And predicted that this will actually make more oil reservoirs feasible for CCUS. I'm not going to show further results for this issue. I'll skip to the next one, which is high CO2 mobility leading to poor sweep efficiency. So let's assume that this is the vertical cross section of the rock where we inject CO2. As we inject CO2, because it's lighter than the oil and it's highly mobile compared to oil, it tends to move at the top of the rock, and it only displaces oil from the top, and it bypasses large quantity of oil, especially near the bottom of the rock. Now, that means the oil recovery is less, means the economics of the project is bad, and the amount of CO2 which we can store here is less, because CO2 didn't even go in the pores here. So the existing solutions are that we inject water with CO2. So if we inject water, the oil which was bypassed by CO2 will be displaced, will be swept with water. So we can improve oil recovery, we can produce more oil. So economics of the project becomes better, but there is a problem. The injected water will occupy some space in the rock, and therefore less pore space is available for CO2 to be stored. So this method does not benefit CO2 storage. So we discovered a new technique at UNSW, and we proposed injection of water saturated CO2. So water saturated CO2 is again a CO2 rich phase, which contains 99% CO2 and less than 1% water present in the vapor phase. So there is no free liquid phase here. The water is only present in vapor phase. So the mechanism of the method is similar to CO2 injection, that initially it's immiscible displacement and then mass transfer occurs at the interface. As a result, some of the CO2 will be condensed into oil. When this happens, the water component of this condensed CO2 will be condensed as liquid, will drop out of CO2 and it will condense as liquid. So as a result, water saturation in the pore will increase. And it's a known fact in petroleum engineering that if water saturation increases, it reduces CO2 mobility significantly. Now, in this pore, CO2 mobility is reduced, and therefore it's harder for CO2 to flow through this pore. And further injected CO2 will go to a neighboring pore which was not swept before, and therefore we increase oil recovery as well as CO2 storage. Now I'm going to show you some results for a different fraction of CO2 injected. The bottom x-axis shows us fraction of CO2 injected. When it is 0, it means it's pure water injection. We're not injecting any CO2. When it is 1, it means it's 100% CO2 injection, no water injection. 0.75 means 75% CO2 injected and 25% water. And this is the methods which we call water saturated CO2, where less than 1% water is injected in vapor phase. And we can see that in terms of recovery, water saturated CO2 or 0.75 fraction of CO2 injected gives us the highest recovery. So these are the best method in terms of recovery. But I would like to highlight here that in CCUS projects, the companies have to purchase CO2 to inject. So therefore, the cost of the project will increase when fraction of CO2 injected increases. Therefore, if we just look at this graph, the economics of the project will dictate using lesser fraction of CO2 injection. And we can see here that because we're injecting larger quantity of water, there is less pore space available for CO2. So here we have only 40% of the pore space stored for CO2. And here, if we inject water saturated CO2, 60% of the pore space can be utilized for CO2 storage. So that means the optimum scenario may not be the one with high CO2 storage. So we are saying that in addition to these technological interventions, we need some policy interventions or policy reforms to promote co-optimization of CO2 storage and oil recovery rather than simple oil recovery optimization. If we do that, we can actually increase CO2 storage in oil reservoirs significantly. So this graph is again International Energy Agency predictions, estimates for storage capacity in oil reservoirs. If we only optimize oil recovery, we'll end up getting a storage capacity of 64 billion tons of CO2. But if we do co-optimization, which I have been pushing for in this presentation, we can go up to 240, which is 4 times larger. And that will really help to achieve CCUS targets to reduce CO2 emissions. But what about future? Perhaps future is maximizing the storage where we do not focus on improving oil recovery rather than we just focus on maximizing storage. But this will require even greater policy reforms. In summary, technical feasibility of CCUS in oil reservoir can be improved by a number of methods, and I have not discussed all of them. There are a number of institutions other than UNSW who are addressing this issue, and they propose different methods or same methods as us. We are focusing on modified CO2 injection and water saturated CO2 injection to improve miscibility and sweep efficiency. But these technological advancements are not enough unless we also do some policy reforms which shifts focus from only oil recovery optimization to both CO2 storage and oil recovery optimization. Thank you very much, and I would welcome any feedback or questions